This is lecture 12 of Computer Science 147, Computer Architecture Study. Our topic for this lecture is there are three distinct sets, like instruction set architecture. We'll talk about that. And then we'll talk about data organization and access, especially with respect to the memories. And of course, register will come along with that part. And we'll review two classic class of design for microprocessor. This is like the style of designing microprocessor. One is called RISC, another is CISC, and they're related to somewhat this instruction set architecture topic as well. So in instruction set architecture, so we have seen already one type at least in this class of lecture 1 has one instruction set architecture of CS147 DV. That's what we called. Maybe in past classes you came across such instruction set architecture either in forms of MIPS instruction set architecture or x86 instruction set architecture or some other processor, whatever that course you attended picked up as an base assembly language or base processor for assembly language experimentation. You have came across that set, right? And if you recall, those things are like have bunch of information about that assembly language and the system. First of all, it clearly and in detail described the set of supported instruction, and also it talked about data storage, like how the memory is conceptually divided into different parts, like to store the code, to store the data, to store the dynamic data, etc., etc. So those things are also part of the instruction set. And while constructing in lecture 11, while constructing a microprocessor, we have seen that our hardware and design for the processor is greatly dependent, greatly influenced by the set of instructions and the underlying assumptions of the memories and the memory division, etc., etc. It depends on those, right? And that basically both of them together is part of your instruction set architecture, right? So what we are talking about here is that like we have started lecture 1 with a predefined set of instructions and the machine characteristics. For example, it is 32-bit machine, it has 32 registers, and couple of registers has some special purpose like pointing to the stack or static data part or the code. There are special register like program counters, high and low, etc., etc. So but question is how and what dictate that specific set of information, how it was constructed, right? And that is the instruction set architecture study. Okay, so basically what happened, like when a new processor is designed, software architect and hardware architect, those two teams comes together and study the market need, study what their processor is targeting to do in a primary section, like if it is a graphics processor versus if it is a network processor or if it is a general purpose processor. And then based on that requirement study, they comes with an common understanding of functions to be supported by the processor. By the supported function means practically it is I'm talking about the supported instruction list. Okay, so based on which list, your compiler designer, assembler designer, and implementer, they design their tools accordingly so that any high level program written in C or Java or such that can be compiled and translated into assembly code, and then assembler will pick up that and translate into corresponding machine code. So this is the software part, right? And hardware designer takes that specification, as we did in lecture 11 by the way, and construct and build an hardware circuitry which supports those set of instruction. In both side, software and hardware side, they look at this specific document, right, which contains a set of instructions, their functions, their machine code formats, what they're supposed to do, and also overall the underlying machine, is it if it is 24-bit machine or 32-bit machine or 64-bit machine, and how the memories are divided into several parts, and what is the convention from the software to store different types of information into that memories, how the data is organized, if it is an, like we'll see later, there is a problem of endianness, big endian and little endianness. Those minor detail, I would say minute detail, are part of instruction set, and whoever comes up with that whole specification document, as I said, it's came up from a joint collaboration between software architect and hardware architect. Their job is functionally as an instruction set architect. Okay, and instruction set architecture is the outcome of that process. Okay, outcome of this process of generating this set of instruction and related detailed information. So what it contains: list of instruction, data storage, and access strategy. Now there are a couple of common elements when a new instruction set is considered to be developed out of nothing, out of thin air, you can say. It's just market driven requirement, that's only the baseline of the whole task. Those elements are mainly like operation codes. What's going to be operation code? Like for example, like we said that okay, every R type operation has operation code 00 and they're distinguished by the function code. Question why, right? We could have decided something else, right? So those considerations, like each decision there has its pros and cons. So people need to understand their implication both in the software side. If we have a common, let's say for example, if we have a common operation code for R type instruction, which is all 0, and they're distinct from one another through the function code, that has certain implication both in the hardware side and the software side, the compiler implementation and assembler implementation. Versus if we say that, hey, there is no function code, just every other operations, like whether it's R type, I type or J type, all of them will have unique opcode. That's another decision, and which is not the wrong decision, which is another option, right? That decision will greatly influence your underlying hardware structure and also software side. Your compiler, assembler need to act accordingly. That's one criteria, right? And then source operand reference. So far in the DV, CS147 DV, you have seen most of the source of the operands are register file, like it is from the register, except for the load word, store word. Those two instructions specifically access the data memory, right? But again, question is why? Like why we restrict ourselves to that? Why don't we actually add memory addresses as an operand of the instructions? You can do that, right? You can make an instruction such that you want to perform access to address from the data memory, add those two data and write it back directly to the data memory without storing it intermediately on the register files. You could have done that, right? We haven't done it for some reason. Of course, like we have this uh, pros and cons study, and we decided at that point CS147 DV should abandon that idea of directly accessing memory from the instruction execution. But there is nothing wrong in doing it, right? You could have done it. You could have added a couple of instruction which has the operand directly coming from the memory. Okay, so that is another things to consider. Then similarly, result operand references means whether my result is going to be stored in the register file or directly into the memory. Those kind of discussion and decision needs to be made, and and again, as I said, each of them has its pros and cons depending on what you are trying to do there. Then also next instruction references, like for us mostly it is from the program counter, like program counter holds pointer to the next instruction. Why such way, right? Can I have an next instruction reference embedded in my current instruction? Why not, right? It's possible to make the hardware in such a way, to make it behave such a way. It's possible to make compiler even to generate such code, machine code for that kind of operations. Okay. Then also, like data source and storage is another consideration. That how big is the memory I'm going to support? Is it like 2 GB memory, 4 GB memory, 64, 1 terabyte memory, something like that? And also like how many register I'm going to support. We just in CS147 DV it was given to you there are 32 register. Question is why there is 32 register. Okay, there can be 64 or 128 or even 16, right? So there must be some decision point of deciding that information, right? And which ultimately comes out as a description of that instruction set architecture, that okay, we fix to 32 register, okay, and that's it. Then we go from there, develop our hardware, develop our software based on that. Then also, like, are we going to embed information directly into the machine code? For example, add I, immediate type of instruction, has a 16-bit data operand right embedded into the instruction. Some architect says, okay, no, I don't want to support it. My operands are always coming from the register or from the memory, right? I don't want to embed it because it is one thing. Of course, it is basically reducing your range. That's a valid reason. Like your machine is 32-bit, for example, CS147, your machine is 32-bit. But for the add I, sub I, immediate type of instruction, your operand 2 is limited to 16-bit range. That's a limitation, right? So someone may not agree with that and may not just abandon that idea of the immediate instructions. There is nothing wrong with that abandoning of the immediate instruction. They have their own logic. Then I/O devices, like are we going to support, for example, I/O mapped I/O or memory mapped I/O, which is pretty straightforward decision in modern age. It's all memory mapped I/O. And also, like, what kind of devices are we using? Is it going to change my processor structure, especially like if some new devices need to be come up and added, then it directly reflect onto processor's capability of getting interrupt from the device for the device operation and stuff like that. And those are some part, interrupt part and interrupt subroutine, etc., should be a part of operating system study out of our scope. But point is that depending on your decision that what type of I/O devices we are going to support, that also influence your computer architecture. which won't be apparently through our projects or like CS147 DV, that the processor we are constructing right now through the project 2 and project 3. They are very simple processor. It does not need any special thing for the IO operations and stuff like that, but real processor has those components as well. So these are, but point is, these are all influential characteristics of different aspects which affect both hardware and your softwares, mainly compiler, assembler. Then instruction representation, right? We say it in CS147 DV that all the instructions are 32-bit long. And we have already seen there, like for some instruction, at least like for example, if it is not a shift instruction, like, then your shift field, that 5-bit field, is unused. Like, this is kind of waste of space, you can say. If someone comes up with that argument, it's a, hey, it's a waste of space, why don't we have a representation for non-shift type of machine code or mnemonics has 27-bit of instruction instead of 32-bit. Why it has to be always 32-bit? It can be like 40-bit, it can be 20-bit, depending on what I'm trying to do. Another great example is your push and pop, right? If you look at that, it needs just the opcode part, right? Rest 26-bit is just thrown away, it is not used. So someone can say, hey, why it has to be a 32-bit format for push and pop when it is sufficient to have the 6-bit to represent that? We are kind of wasting the space in the memory. That's a valid argument, right? And in fact, there are machines which supports variable length instructions. Okay, we'll see that in towards the end of this lecture. So this is another consideration, like, am my machine code going to be a fixed length or of a variable length? Also, bit field definition and identifying the instructions on the element. Like if you recall, art type, for example, has like first 6-bit as opcode, and then next 5-bit is RS, then next 5-bit is RT, then next 5-bit is RD, then next 5-bit is your shift amount, and next 6-bit is function code. How do we decide it? We could have done it other way, or any way we could think of, like, but point is that some point of time, with some discussion, it has been fixed. All right, but if your instruction set is not even there when you are trying to build up that instruction set, these points comes up in that discussion, that which field with identify what, right? Someone can say, okay, I will place my machine code at the LSB side compared to the MSB side. Nothing wrong with that, right? Also, instruction types, like data processing instructions type. Am I going to support like a matrix operation versus linear data operation versus array data type of data operation? These are comes in, like CS147 is simple data operation. It doesn't handle matrix, it doesn't handle vector type of data. So so those consideration comes in place. Data storage plays another movement, right? How much memory I'm going to support, and how much text or code part, how big would be the text area in that memory, how big would be the static data part in the memory, how big would be the dynamic data part of the memory, and so on and so forth, right? And also program control, how we jump from one place to another. What would be our mechanism for function calling and function implementation? Those are all also part of your type of instruction that we are going to support. And as you saw through the lecture 11, that this type of instruction will greatly influence your hardware implementation. For example, if we didn't have push and pop instruction in the data set, in the instruction set for one CS147 DV, we wouldn't have to worry about or construct the data path and corresponding control path for the push and pop operation. Our circuit would be much simplified than what it is today, right? Which supports push and pop. So that's the kind of influence you have on your hardware. Also, on the software side, it has influence, right? In the software side, compiler, in early case, it didn't have to deal with push and pop code generation. Now it's going to have to deal with push and pop code generation. That's a change in compiler as well. So, most disputed area in the computer architecture study is this instruction set, right? Because there is no clear winner. Everyone, and every proposal has its own pros and cons. Okay. First of all, these debates are operation repertoire, right? So this is basically your list of operation you are going to support, data types, instruction formats, every other field, whatever we discussed so far, everything can be debated there. Most disputed part is probably your data organization in the memory and addressing mode of an operands. So we'll look into that. This is our next part: data organization in the memory, and then data access from the memory. Okay, these are two most disputed area in the instruction set architecture study or instruction architecture problem solving.